Pluto's way will undoubtedly cause issues. From the beginning, Pluto's circle converges with that of another planet. Pluto, the strange and little planet found in the farthest corners of our solar system, has turned into a hotly debated topic in cosmology. Ongoing updates propose a potential impact with Neptune, raising alarms among researchers and space enthusiasts. Renowned figures such as Neil deGrasse Tyson and Michio Kaku have expressed concerns regarding the potential consequences of this celestial encounter. But how did Pluto end up on a crash course with Neptune, and what might this cosmic conflict mean for Earth? Join us as we explore the details of how a massive event with Neptune could have occurred and why researchers are unsettled by this cosmic anomaly. Pluto, once celebrated as a full-fledged planet, underwent a dramatic reclassification as a dwarf planet, largely due to its irregular orbit. Despite this downgrade, Pluto continues to fascinate and spark curiosity within the astronomical community. Recent warnings from prominent scientists, such as Neil deGrasse Tyson and Michio Kaku, suggest that Pluto's path could intersect with that of Neptune, implying a possible risk of collision, with serious ramifications for our planet. Pluto's journey around the Sun is remarkable due to its unique characteristics. Its orbit is exceptionally long, taking a staggering 248 years to complete. Since its discovery in 1930, Pluto has not yet completed a full revolution around the Sun. What makes Pluto even more captivating is the extreme elliptical shape of its orbit, a stark contrast to the nearly circular orbits of the major planets. Moreover, Pluto's orbit is tilted at an angle of 17 degrees relative to the ecliptic plane, resulting in a steeper incline compared to the paths of other planets. This combination of inclination and elongated orbit adds complexity to its motion. A fascinating aspect of Pluto's orbit is its repeated convergence with Neptune's orbit. Every few centuries, Pluto's path brings it closer to the Sun than Neptune, challenging our expectations of their relative positions in the solar system. Further investigation reveals that Pluto's orbit is far from a perfect circle. Rather, it follows an elliptical path, meaning its distance from the Sun varies significantly throughout its orbit. At its closest point, Pluto comes within about 30 astronomical units of the Sun. However, at its farthest, it stretches to more than 49 astronomical units, nearly twice the distance of Neptune from the Sun. Additionally, Pluto's orbit is inclined at an angle to the orbits of other planets, adding another layer of complexity to its relationship with Neptune. This inclination plays a crucial role in how Pluto and Neptune interact. When their orbits intersect, their gravitational forces influence each other, gradually altering their trajectories. This dynamic between Pluto and Neptune highlights the interconnected nature of the solar system, where each planet exerts gravitational forces that affect the movements of others. Over the years, advancements in observational instruments have allowed astronomers to track Pluto's movement with greater accuracy. This has led to a better understanding of its orbit and its potential impact on the overall stability of the outer solar system. Although the likelihood of a direct collision between Pluto and Neptune remains low, the possibility is still under examination. Continuous monitoring persists, as the potential consequences of such an impact could be dramatic. Despite Pluto's small size and distant location, it continues to be a subject of interest for scientists and space enthusiasts alike. A key question that arises is, why hasn't Pluto collided with Neptune already? The answer lies in the gravitational influence of other planets. From the moment Pluto was discovered, astronomers have been working to understand its trajectory. Unlike most planets, which maintain a consistent orbit along the ecliptic plane, Pluto's orbit stands out due to its steep angle and elliptical shape. The mystery deepened when it became evident that Pluto's orbit crosses Neptune's. Despite this apparent danger, Pluto's orbit remains remarkably stable, illustrating the sophisticated mechanics that govern space. Studying the interactions between Pluto, Neptune, and the Sun presents a formidable challenge for astronomers. Predicting their movements requires a deep understanding of how they influence each other's trajectories. To tackle this challenge, scientists rely on equations such as apsidal libration, scope libration, VSOP, variations séculaires de orbites planétaires, and Steve's Kaplan isolation to solve this cosmic puzzle. Apsidal libration, for instance, is crucial in maintaining the stability of planetary orbits. When Pluto crosses Neptune's path, it remains at least 90 degrees away, preventing a direct collision. Scope libration ensures that when Pluto approaches Neptune or other massive planets, it is positioned above their path, reducing the likelihood of an impact. The VSOP oscillation, named after researchers von Zippel, Steves, and Kaplan, explains why Pluto's orbit appears unusual, yet remains stable over time. Although space may seem chaotic, there are underlying pattern formations that help maintain order. These patterns prevent Pluto from crashing into Neptune or drastically altering its orbit. The concept of orbital chaos, which describes how a celestial body's trajectory is highly sensitive to its initial position, is clearly demonstrated by Pluto's orbit. Even small variations in Pluto's position or velocity can have significant effects over long periods. Scientists use advanced virtual simulations to model Pluto's interactions with other celestial bodies, such as Neptune, and to explore the outcomes of even minor shifts in its trajectory. In the late 1980s, these simulations revealed something intriguing. Despite the apparent stability of Pluto's orbit, it can still behave unpredictably. A tiny adjustment in Pluto's initial position or velocity could lead to significant changes in its orbit over time. However, even with these uncertainties, Pluto's orbit remains stable for billions of years, suggesting that despite its erratic appearance, it follows an underlying order. The eccentricity of planetary orbits, such as Pluto's, makes it challenging to predict long-term changes with certainty. These models require highly precise initial conditions, as even small errors in data can produce vastly different outcomes, making accurate predictions incredibly difficult. Understanding Pluto's orbit is essential, particularly when considering the potential for a future collision with Neptune. The stability of Pluto's orbit. Despite its seemingly chaotic motion, Pluto's orbit follows a pattern influenced by the gravitational interactions of the solar system. One of the most critical factors in preventing a collision between Pluto and Neptune is a 3:2 mean motion resonance. This means that for every 3 orbits Neptune completes around the Sun, Pluto completes exactly 2. This resonance ensures that the two celestial bodies never come close enough to collide, despite their overlapping orbits. The role of resonance in celestial mechanics. Resonance is a crucial concept in celestial mechanics, acting as a stabilizing force in the solar system. The gravitational influences of larger planets, particularly Jupiter and Saturn, also play a role in maintaining Pluto's orbital stability. The intricate balance of these forces prevents Pluto's orbit from deteriorating into chaos. Pluto's interactions with Neptune are further influenced by orbital precession, a slow, continuous change in the orientation of its orbit over time. This precession, combined with the 3:2 resonance, ensures that whenever Pluto crosses Neptune's orbital path, the two planets are never in the same location. Could Pluto's orbit change in the future? While Pluto's current orbit appears stable, astronomers must consider the long-term evolution of the solar system. Over millions or billions of years, small gravitational perturbations from other celestial bodies, such as passing stars or the influence of distant objects in the Kuiper Belt, could gradually alter Pluto's orbit. One of the biggest concerns in planetary dynamics is the possibility of chaotic evolution. While Pluto's orbit remains stable for now, even a slight variation in the gravitational forces acting upon it could lead to unpredictable changes over immense timescales. Recent studies using high-precision computational models suggest that Pluto's orbit is unlikely to destabilize within the next 100 million years. However, the long-term fate of Pluto, Neptune, and the outer solar system remains a topic of active research. What would happen if Pluto collided with Neptune? If, hypothetically, Pluto's orbit were to change and lead to a collision with Neptune, the consequences would be dramatic. Given Pluto's relatively small size compared to Neptune, it would likely be absorbed into the gas giant's atmosphere or torn apart by Neptune's immense gravitational forces. The debris from such a collision could potentially create a new ring system around Neptune or scatter into the outer solar system. However, as previously stated, This scenario remains highly improbable due to the existing gravitational safeguards that maintain Pluto's position. Pluto's significance in modern astronomy. Despite its reclassification as a dwarf planet, Pluto continues to play a vital role in our understanding of celestial mechanics, planetary formation, and the dynamics of the Kuiper Belt. The New Horizons spacecraft, which flew past Pluto in 2015, provided unprecedented insights into its surface, revealing a world with glaciers, mountains, and a complex atmosphere. These discoveries have reinforced Pluto's status as one of the most fascinating objects in the solar system. Furthermore, Pluto's orbital behavior serves as an excellent case study for astronomers studying exoplanets, planets orbiting other stars. Many exoplanetary systems exhibit resonant orbits, similar to Pluto and Neptune, suggesting that the mechanisms maintaining Pluto's stability may be common throughout the universe. Conclusion. While Pluto's orbit is unusual and complex, it remains stable due to the intricate gravitational interactions within the solar system. The resonance with Neptune, combined with the influence of larger planets, prevents any immediate risk of a collision. However, the long-term evolution of Pluto's orbit remains an open question. As astronomical techniques and computational models continue to improve, scientists will be able to refine their predictions and deepen our understanding of the delicate balance that governs planetary motion. For now, Pluto remains a distant but captivating world, continuing to challenge and expand our knowledge of the cosmos. Neptune. This information adds to a more extensive comprehension of how our solar system works. Pluto's orbit serves as an illustration of how seemingly chaotic paths can ultimately reach equilibrium. Guided by the forces of gravity and motion, we must continue to observe and study these celestial mechanics to gain a better understanding of our position in the universe. Pluto's orbit offers a perfect example of the unpredictable nature of space. Pluto's orbit is unlike that of the other planets, with its elliptical shape leading to unusual encounters with Neptune. This irregular movement makes it challenging to predict the long-term dynamics of the system. However, gravitational forces play a crucial role in preventing Pluto and Neptune from colliding. Gravity, a force that attracts objects to each other, ensures that despite their crossing orbits, the two bodies remain separated most of the time. These interactions reflect the delicate balance of forces at work in space. The possibility of a collision between Pluto and Neptune, while unlikely, would be a significant event with massive consequences. Such an event would dramatically change our understanding of the solar system. Though space exploration has advanced significantly, Pluto's orbit serves as a reminder of the many uncertainties that still exist. Scientists continue to study Pluto's path to better understand how large planets influence its motion. This knowledge is essential for comprehending the complex relationships between celestial bodies and how their movements can impact one another. Despite the unpredictable nature of Pluto's orbit, some of the world's leading scientists, like Neil deGrasse Tyson, have speculated that Pluto might one day collide with Neptune. Tyson, a prominent astrophysicist, sees Pluto's reclassification as a dwarf planet as a necessary step in recognizing the importance of continued exploration and study. He believes that Pluto's unusual orbit underscores the fact that there is still much to learn about space and the forces at work within it. According to Tyson, the mysteries of space make studying it so captivating, and he encourages others to engage with the fascinating intricacies of celestial mechanics. Tyson, along with other experts, is concerned about the potential dangers posed by Pluto's erratic path. If a collision between Pluto and Neptune were to occur, it could have catastrophic implications for our solar system. The energy released from such an event would be immense, and the debris scattered throughout space could have far-reaching effects, potentially even impacting other planets and moons. Neptune itself would be affected, and its orbit could be altered, further complicating the dynamics of the outer solar system. Renowned theoretical physicist Michio Kaku, known for his work in string theory, also provides valuable insight into space exploration. Kaku believes that studying phenomena like Pluto's orbit is essential for understanding the broader principles of celestial mechanics and theoretical physics. He suggests that examining Pluto's interactions with Neptune can help scientists navigate future space missions more safely. Kaku also emphasizes the importance of understanding gravitational forces in the context of space exploration, as they have the potential to shape the future of how we explore distant worlds. Kaku's work in string theory, which seeks to explain the fundamental forces of the universe, aligns with his interest in Pluto's orbit. A collision between Pluto and Neptune could provide valuable data that would contribute to our understanding of gravity and space-time, concepts central to string theory. Although such an event would have minimal direct impact on Earth, it could offer a unique opportunity to study the behavior of fundamental forces in extreme conditions. As scientists continue to explore the depths of space, the unpredictability of planetary interactions becomes more apparent. The study of celestial dynamics, such as the intricate gravitational relationship between Pluto and Neptune, offers significant insights into the fundamental laws of the universe. By continuing to monitor and study these phenomena, we move closer to understanding the vast and complex nature of the cosmos. The gravitational dance between Pluto and Neptune highlights how even distant planets can influence each other. These celestial bodies exert gravitational forces that, over long periods, can subtly but significantly shape their orbits. While a direct collision remains unlikely, the possibility cannot be entirely ruled out, leading to ongoing interest and observation from the astronomical community. Scientists believe that understanding these forces may one day allow them to predict and potentially mitigate the risks posed by such cosmic events. One fascinating aspect of planetary motion is how seemingly random or chaotic interactions can lead to stable, predictable patterns. This phenomenon is particularly evident in the case of Pluto, whose orbit may appear erratic, but is actually governed by precise gravitational forces. These forces help prevent Pluto from colliding with Neptune, despite the apparent overlap in their paths. The delicate balance between the gravitational pull of various planets and Pluto's orbit keeps the dwarf planet on a stable, yet complex course. Understanding this intricate relationship is essential for advancing our knowledge of the broader planetary system. As scientists continue to study the unique characteristics of Pluto's orbit, they also look toward other areas of space exploration. The study of systems like the TRAPPIST-1 system, which contains multiple Earth-sized planets, helps astronomers understand how gravitational forces between planets can lead to orbital resonances and, in some cases, increase the chances of a planet's path becoming unstable. Although the TRAPPIST-1 system is not currently experiencing any collisions, scientists remain vigilant in tracking the movement of planets in these crowded environments to better understand potential risks and how they may evolve over time. Meanwhile, astronomers are also focused on understanding the behavior of rogue planets, those that wander through space without being bound to a star. Rogue planets, which drift through space without a parent star, add another layer of complexity to our understanding of planetary motion. Unlike Pluto and Neptune, whose interactions are shaped by the gravitational forces of the Sun and other celestial bodies, rogue planets move unpredictably, influenced only by the occasional gravitational encounters with other massive objects. Studying these wandering planets could offer insights into planetary formation, stability, and even the potential for life beyond our solar system. The study of planetary orbits, particularly those as unusual as Pluto's, also has practical applications. By understanding the gravitational interactions between celestial bodies, scientists can refine models that predict the movement of asteroids and comets, some of which may pose a threat to Earth. In recent years, space agencies have developed strategies for planetary defense, including asteroid deflection techniques. The ability to predict and influence the trajectories of potentially hazardous objects is a direct result of studying celestial mechanics, much like the principles governing Pluto and Neptune's complex relationship. Additionally, learning more about Pluto's orbit and its interactions with Neptune helps astronomers understand the stability of other distant planetary systems. Observations of exoplanetary systems, some of which feature gas giants in highly eccentric orbits, show that gravitational forces can lead to planetary migrations, collisions, and even ejections from their original orbits. By comparing Pluto's interactions with those seen in exoplanetary systems, researchers gain a broader perspective on how planets evolve over time. As technology advances, scientists continue to refine their understanding of gravitational forces, planetary resonances, and the long-term evolution of our solar system. Future missions to the outer solar system, possibly including another mission to Pluto, could provide more precise data on the forces that shape planetary orbits. Advanced telescopes, both ground-based and space-based, are also improving our ability to track distant celestial bodies with unprecedented accuracy. Despite being classified as a dwarf planet, Pluto remains an object of significant interest. Its orbit, while seemingly chaotic, is a key example of the underlying order that governs celestial mechanics. As scientists uncover more about Pluto's path and its interactions with Neptune, they continue to unravel the mysteries of the cosmos, reinforcing the idea that even the most unpredictable movements in space are governed by fundamental physical laws. The study of Pluto's orbit is more than just an examination of one celestial body. It is a testament to the vast and intricate gravitational relationships that define our universe. By continuing to observe, analyze, and theorize, astronomers inch closer to answering some of the most profound questions about planetary motion, cosmic balance, and the forces that shape the very fabric of space-time.